Exponential growth and decay. So exponential growth happens a lot faster than like a slope of a line that's positive. And decay, the same thing. It follows an exponential curve where we're multiplying instead of adding on. So for example, one of the exponential equations that's most commonly used is a constant times e. E is just a number. If you type it in on your calculator, it's probably an e to the x. So if you press e to the 1, you'll see it's like a 2.718 and goes on and on. So kind of like pi, a constant like pi. To the k, often representing rate, times time. And time is usually measured in years. P of t, in this case, if we're looking at the population equation, this side is often the end result. It's the y value you're looking for, or the function value you're looking for. This often represents the initial value. And oftentimes when you talk about an initial value, it has this little zero down here. And you say this p sub naught. So you're starting, it's just a constant. That sub naught does not mean times zero or anything like that. It's just identifying that this p sub naught has to do with the population, but it's the initial population or beginning population. K is your rate, just a constant rate. Sometimes it's represented as R times T. Now it really doesn't matter what variables are here and here and here. It's the same basic equation. So let's see how this equation works and how we can use what we know about logarithms and exponents to solve for some of these values. So in 1992, the population of the United States was 249 million. So with a growth rate of 0.9%, that means per 100, how many years will it take to reach a population of 300 million? So you can imagine scientists and community planners would want to know this kind of thing if they're planning a community and base it on a certain rate. So you just set up the equation where you have 249 is your initial population. You want to end with 300 million. And then we have E, and the reason we don't have to put million here is because if we divide both sides by a million, we'll end up with just 300 and 249. E to the 0.009t. I have to write this percentage in decimal form. And if you forget how to do that, all you have to do is remember that percent is per 100 and do 0.9 divided by 100 on your calculator. Times t, that's your number of years. You want to know t, so t is your unknown, and it's in the exponent, which makes it a little bit tricky. Now you can't multiply 249 times e, because e has this exponent. It's not just e, it's e to a power. So don't multiply this initial value times e. The way you want to do it is to separate it so you just have the exponential part of the equation. So divide both sides by 249. So I have 300 over 249 is equal to e to the 0.009 times t. So now this is isolated. And this looks a lot like exponential equations we've seen before, where there's an unknown in the variable. When there's an unknown in the variable, one way to do it, you could either write it in logarithmic form, or you could take the log of both sides. So I took the log of both sides here, and I took the natural log. So this is log base e of 300 over 249, and I took the log base e for a reason, because this e right here is going to make it easier for me to take the log base e. So here I have log base e of e to the 0.009t. So this right here is log base e of e. Remember, the e is not written. So ln of e is equal to log base e of e. Notice these are matching. The bases are matching right here. And so just by the inverse function, I know this whole side is just equal to 0.009 times t. So I still have log 300 over natural log of 249 is equal to 0.009t. And then just moving right up here, to solve for t, we just divide both sides by 0.009. So I have a log of 300 over 249 over 0.009, and that's equal to t. Now I encourage you to try this on your calculator. Make sure that you know how to input it. Depending on your calculator, you may have to enter this first and then hit the log button. Or when you hit the log button, make sure that you have that whole thing you're taking the log of. And so that's about 20.7 years. So it's already happened if you look at how old this is over here. Yeah, already happened. So in 10 years it would be 2002, and then in 20 years it would be 2012. So it's already happened that the population reached 3 million, and that is equal to RT. So let's look at another example, and this is a half-life example. So half-life is an example of exponential decay. So what's happening in a half-life, oftentimes it's used with medicine or radioactive decay. So if you put a certain amount of medicine in you, it cuts by a half the amount that's in your system and continues to do that. So for example, if we're just looking at the half-life of a medicine, let's say a medicine has a half-life of 5 hours. That means it stays in your system for 5 hours, and then after 5 hours it's only half the amount in your system, and then again cuts in half and again cuts in half. So if we started with 80 milligrams and the half-life was 5 hours, after 5 hours you would only have half that amount, or 40 milligrams. And then after 5 more hours you would only have 20 milligrams in your system, and after another 5 hours you would only have 10 milligrams, and it would continue until it's a very, very tiny amount. Never zero, because you're always cutting it in half. Luckily your body has other ways to dispose of this kind of medicine. But half-lives are very helpful in biology and medicine and chemistry when you're talking about the half-life of radioactive elements. So for example, you can notice this equation is very much the same. Your book uses this equation instead of the population equation, P for population, and I'm not sure why they chose N. I've seen K there, but regardless, these are just values right here. This is your initial value, your Y is your ending value, K is your rate, and T is your time. And again, we have that E, which is just a number. So the half-life of radium, radium is a radioactive element that's unstable, so it decomposes at a constant rate, kind of falls apart, is 1,620 years. So an initial amount of radium, if you have an initial amount, after 1,620 years, you only have half that amount left. And so what I can do here is kind of a little trick. It doesn't really matter what my initial amount is. I'm going to have half of that initial amount after 1,620 years. So instead of Y here, I just put Y is equal to 1/2 N, because whatever I started with doesn't really matter. I'm going to end up with a half of it. And the reason I want to do this is because I can divide both sides by N now. N is not attached to this exponent up here. And when I do that, I just get 1/2. So it doesn't really matter the initial amount in this equation. Now I'm going to solve for K here. So I have e to the K times this is equal to 1/2. Well, now when I have an unknown in the exponent, I want to take the log of both sides or write it in exponential form. I took the log of both sides. So I wrote it in exponential form. So I did log base E of 1/2 is equal to 1,620K. Now I could have also taken the log of both sides, the natural log of both sides, like I did in the other one. You would end up with the same thing. I'm just showing you kind of a different method here. So I just rewrote this exponential equation in logarithmic form. Log base E I know is ln, and 1/2 I wrote is 0.5 just because it's easier to put in my calculator. So log base E of 1/2 is the same as ln of 0.5. And that's equal to this. Solving for K, I just divide both sides by 1,620, and that's equal to K. Now I solve for K. Notice that it's a negative number, and that's because this represents decay. So this negative number is going to make E be in the denominator. So now I have an equation, Y equals N, E to this rate, it's kind of long there, times T. So if I'm given an initial amount, and either the ending amount or the time, I can solve for either one of those variables. So the reason I wanted to solve for this is because now if I'm given an equation, just knowing the half-life, if I'm given a certain amount, like maybe I want 1/5 the initial amount and I want to know how much time it's going to take, I can use this equation to find that out. I would just substitute this with 1/5 N, divide by N, and then I'd solve for T much in the same way I solved for K. So some of these questions are two parts. You initially have to solve for k, and then you have to input what the question is actually asking. So t is usually measured in years unless they tell you differently. So now let's look at a problem with compounding. And this is just two of the possible ways to compound. There's many, many other ways as well, but this is all we're covering in this section. We have compounded continuously and we have compounded annually, so once a year. So say you put $400 in the bank at 6%. How long will it take to double in two different situations? A, if it's compounded continuously, and B, if it's compounded annually. So compounded continuously just means you are continually earning that interest over time. You're just continually earning the interest, and then you're earning interest on whatever interest you've earned, and you just continue to do that to a total of 6%. Annual interest is once a year, they take the money that you have and they add 6% to it. And then you don't get another interest until that next year. So here is our compounded continuously formula. A equals P e to the RT, looks just like our other exponential equations we've been working with, where P is the principal or initial amount, A is the ending amount, E is just our number, R is the rate in decimal form, and T is time. Our other equation, A equals P 1 plus R, and it's a growth equation, so that's why it's plus R. If it were a decay, it would be minus R to the T power, and T is in years. So you're just taking this, and once a year you're compounding the interest. So our initial amount, let's start first with the compounded continuously. You're starting with 400 and you're ending with 800. Now they really didn't even have to give you that $400. It's going to take the same amount of time no matter what you start with. And you can see that because if they gave you $1,000, this would be $2,000, and when you divide that, you're going to end up getting 2 regardless. So here I have 400, here I have 800. It's just a specific example. And I just divided both sides by 400 because remember, you can't multiply the 400 times the e because e has that exponent, it's not just e. So dividing both sides, I have 2 equals e to the 0.06t. Now this time, instead of writing it in logarithmic form, I just took the log of both sides. So the log of 2 times the natural log, this is natural log of 2, equals the natural log of e to the 0.06t. So then I'm going to take that exponent and I'm going to bring it out in front like I can with logarithmic properties. ln of e, or I notice that ln of e is log base e of e, and I can see that log base e of e, I have matching bases, it's just this. Either way you do that. If you brought this out in front, you would know ln of e is 1 and it's just 0.06t. On this side I still have ln of 2. And then you can just go ahead and solve for t by dividing by 0.06. So ln of 2 divided by 0.06 equals t. And so that's approximately 11.6 years. And we would imagine that b is going to be similar to that. So b, same sort of thing. My principal's 400, my ending amount is 800, but again it doesn't really matter because when I do that division, I'm always going to get 2. And then I have 1.06. I'm adding that 1 plus the 0.06. I have to remember to write that in decimal form to the t. Now, since there's no e in here, you could still use natural log. It doesn't matter. I just used log base 10 to show you something a little bit different. You don't have to use log base 10. I'm not going to use log to the base 1.06 because it's kind of a weird base. And so I want to be sure I can do it on my calculator. So again, if you used ln, it would be the same answer if you'd use natural log. So I encourage you to try that if you are a little bit skeptical. So log of 2 is equal to log of 1.06 to the t power. Again, I'm going to use properties of logarithms, and I'm going to move that t out in front and multiply it times that log. So I have log of 2 is equal to t times log of 1.06. Now log of 1.06 is just a number, so to solve for t I can divide both sides by log of 1.06. So then I have log of 2 over log of 1.06, and that's equal to t. And putting that in on my calculator, I have t is equal to 11.9 years. So 0.3 years, so 3/10 of a year earlier, you will double your money if you have it compounded continuously rather than annually.